let's compare the directions in problems 10, 11, 12, etc. with the previous directions. Notice that it starts out the same. Determine if the limit exists. If so, find the limit. If not, justify your answer. Notice the absence of also sketch a graph of the function. And that's because some of these are more difficult to sketch. We don't have parent function background on 10 and 12 to produce a graph without a calculator. All right, so 11 we would be able to produce the graph without a calculator, but 10 and 11 would have to, let me go back there, we'd have to use a calculator. I'm not quite sure what happened there, but hopefully everything's okay now. There's just going to be sometimes technical difficulties with this technology. All right, so we're determining if the limit exists. If so, find the limit. If not, justify your answer. All right, so for number 10, the first thing we're going to do is try the direct substitution. That is, plug 3 in, even though we're approaching 3 from the right side. All right, so that would be negative 3 plus 4, all over 3 minus 3. The result is 1 over 0. We know that's going to be a does not exist because that's a vertical asymptote. All right, so we didn't even have to get down to the nitty-gritty. We didn't have to plug in numbers close to 3 to the right of 3. It was easier to work with 3 as opposed to 3.1, 3.01. So that's the first thing you want to try is plugging in straight the number. All right, number 11, plug in 3. Notice I'm losing the limit statement when I do a substitution in. Plug in 3. If we have to, we'll choose numbers close to 3 to the right of 3. But we're not going to have to do that because we get undefined. So this limit will not exist because there's going to be a vertical asymptote there. This is the one I said that you could graph without a calculator. Let's revisit that. That is the reciprocal graph, shifted right 3. So here's our vertical asymptote. The 2 vertically stretches the graph, but the negative is going to actually reflect it. So instead of having branches here and down here, we would then have branches here and a branch here. So if we were trying to be descriptive about what kind of asymptote it is, we can look at this visual and say, well, here's 3. If I'm approaching 3 from the right, I'm approaching a negative infinity. So that would just be a little more descriptive, a negative infinity here. All right, going back to 10 now, like I said, it doesn't say to sketch the graph, but what if we did want to know what infinity we're approaching because of that vertical asymptote? Well, that would require us then actually plugging in a number close to 3 but to the right of it. And if we just kind of did that mentally, plug in a number that's close to 3 to the right of it, and 4 is too far away. So if I plugged in 3.1 here, all we care about is positive or negative output. The denominator, when you subtract and do the computations, is going to be positive. When you plug in 3.1 and make it negative and add 4, you're still going to have a positive numerator. So for this particular problem right here, positive divided by positive would result in a positive answer, meaning that the vertical asymptote that we're approaching is the positive one, the positive infinity. All right, let's look at 12. All right, I notice I'm approaching 5 from the left, like 4.9, 4.99, etc. But let's just go ahead and plug in 5 and see what happens. It's nice because the numerator is not going to be 0. The denominator will be 0. Come back. So 4 over 0 is does not exist, limit, vertical asymptote. Okay, well, which vertical asymptote or which infinity are we approaching? If you wanted to further investigate, you don't have to unless you're requested. Let me make that clear. It's just so much easier working with the integer. Alright, let's plug in like 4.9. Remember, we're losing the limit statement, so 4.9 minus 1. It's going to be a positive numerator. So the opposite of 4.9 plus 5. Okay. So I know I'm going to have 3.9, a positive number, over 0.1, and that looks like the answer is going to be 39, but it doesn't matter what it's going to be. It just means that you're going to approach the positive infinity because of the calculations. And again, if you're afraid you're going to make some mistakes, you might want to then in a second example plug in something closer to 5 than 4.9, so that would be like 4.99. but the output should still be the same. Okay, otherwise we're just done when we say does not exist vertical asymptote. Okay, I think we've explored all the situations that we need to as far as a limit not existing at the case where we have a vertical asymptote, an asymptotic discontinuity. So now let's move on and look at some jump discontinuities and limits that fail to exist there. Okay, paying attention to the directions, determine if the limit exists. If so, find the limit. If not, justify your answer. Look, we're returning to sketching a graph of each function. Okay, proceeding the way we did in the previous examples, let's just do a direct substitution. Let's plug 0 in. Notice it's not from the left or the right. Let's just plug 0 in. So what results is indeterminate. We're going to get 0 over 0. That's indeterminate. Further investigation must take place. Okay, and I want you just to kind of process this for a minute. If you get 0 over 0 when you're performing a limit action, 0 over 0, what that means is we could either have a jump discontinuity or we could have a point discontinuity. And it's important to note that for a jump discontinuity, the limit's going to fail to exist, but for a point discontinuity, if all I have is a hole, that my limit is going to exist as I approach that hole. So it's important to do some further investigation. So okay, what we need to do here is either find the answer analytically, or excuse me, numerically using numbers, or use a graph to help us with the answer. All right, so the first thing I do is I look, can I graph this without a calculator? I can. Now, if I had a calculator, there's no question. I'm just going to go and input this into y equals and look at the graph to see if the limit exists by exploring behavior on the graph close to 0 on either side of it. But I do know what this graph looks like. So using a graph to help us. Alright, as I approach 0, and this means I have to look at behavior on both the left and the right hand side. Okay, as I approach 0 from the left, so I'm to the left of 0, I'm on the graph, I'm getting closer to x values of 0, I can see that on this here and there function that my left hand limit is -1. So we might want to, with our work, put down here, well, the limit as x approaches 0 from the left of this function, the y values are -1. Alright, let's explore the right hand limit. So I'm just going to put a little semicolon here. Try and squeeze it in all right here. As I approach 0 from the right on this function, and notice that I keep writing the function down, you need something here, whether you use f of x or the specific equation. Well, if I approach 0 from the right side of 0, that means I'm walking back this way. Okay, those y values are 1. We have a jump discontinuity because the left limit does not equal the right limit, because these two numbers aren't the same exact number. We have a jump discontinuity. We know the limit fails to exist. So determine if the limit exists. No, it doesn't. If so, find it. If not, justify your answer. So I'm going to come down here and kind of clean it all up. So this limit does not exist. And I'm going to put because, I'm going to abbreviate, BC. Okay. And the notation we're going to use is actually what we have up here. The left limit does not equal the right limit. You could probably use those words, left limit does not equal right limit, but it's much better to support your work with these limit statements. Okay, and here what you're saying is the left limit does not equal the right limit. Okay, and your work up here supports this statement that you have down here. So this is jump discontinuity, the limit fails to exist, and the explanation on that is going to be because the left limit does not equal the right limit, and this is the correct notation. Okay, let's take a look at 14. Alright, let's evaluate this limit analytically first, see what we get. Insert -1, add 1, you're going to get the absolute value of 0, which is just 0. Insert -1, you're going to get 0. This is indeterminate. Further investigation, either plug in numbers to the left and to the right of -1, see what those outputs are. Okay, if those outputs are not exactly the same, okay, then we know we have this situation, the limit fails to exist. Numerically, that's kind of tedious. That's why I'm relying on a graph. Okay, so I'm going to draw the graph. It's the here and there function shifted to the left 1. So here's negative 1. Okay, and we know that that's indeterminate here. All right, so that means that above negative 1, we're going to start the open circle and go to the right. Below negative 1 vertically, we're going to start the open circle and travel to the left. Okay, these y values are still the same. This is 1 and this is negative 1. Okay, we have to evaluate limits from the left and the right. As I approach negative 1 from the left, negative 1 from the left, my y values are negative 1. I'm going to put a semicolon here. Okay, let's look at the right hand limit. Okay, sorry it's kind of sloppy, it's just this stylus. Okay, don't forget to put the function again here. Okay, just visually, as I approach negative 1 from the right, my y values are positive 1. These two numbers are not identical. That just means this graph will never come together. Okay, we have to make a jump. So from that, now we know that the limit does not exist, and we know our explanation why it doesn't exist. And it's not okay to say a jump discontinuity. That's kind of an informal description of what's going on. Okay, it's more about your limit statements. So as I, oh sorry, this should be negative 1. The limit as x approaches negative 1. Is it does not exist because the left limit doesn't equal the right limit. I know it may seem kind of tedious to kind of write all this, but you know what, it's good practice because things have to be written, and it just allows you that practice. So the limit from the left does not equal the limit from the right. I promise I write much neater than this. It's just, it's kind of challenging with the stylus. Alright, let's observe number 15. Plug in 5, again indeterminate. It's the here and there shifted to the right 5. The result is going to be the same. The same meaning that the limit won't exist. So we'll just bypass all of this. But if you need extra practice sketching a graph, I encourage you to do so and then confirm with the calculator. Okay, you're going to get a does not exist because the left limit does not equal the right limit. In case you're wondering here, you don't have to actually show that the left limit equals negative 1 and the right limit equals positive 1. This would suffice as a adequate, I guess, complete explanation. Because we all know what this graph looks like out there in the calculus world. We all know what that graph looks like, and so we can draw from that, and this would be just enough. Alright, before moving to the last two examples, let me just make this comment about any of the problems 13, 14, and 15, and I'm just going to do that right here. And you can just watch and not write if you want. I just want you to know that it's important to pay attention to the direction in which you're approaching that x value. So for example, I'm looking at number 13, and I'm going to modify it just slightly. Okay, what if this was the problem presented to you? Okay, notice the comparison of what I just wrote down here in problem 13. The change is that I'm being real descriptive about which side to approach 0 from. If I'm approaching 0 from the left, I'm saying don't look at the entire graph, only look at x values to the left of 0. Well, graphically we know that that answer is negative 1. So if this was your problem right here, you don't want to say does not exist because we're not looking at both sides of 0. We're only looking at one side. And so our left hand limit exists, our right hand limit exists. but the limit as you approach 0 from both sides does not exist. So this would be certainly something totally acceptable. So I guess my point is pay attention to any superscript right here, because just because you see this here and there function doesn't mean that your answer is always D and E. It's only if there's no superscript here. Okay, so for these last two examples, I might encourage you to, at least with 16, try and graph this piecewise function without a calculator. Notice that all of the pieces are very manageable. We have two linear functions, top and bottom piece, and then the middle one here is just a point 2, 2. So that would be easy to manage without a calculator. If you look at 17, the top piece is the reciprocal function, not bad. But the bottom piece is quadratic, and it's not in vertex form, so I can't really quickly identify the vertex, so it would make it more challenging to graph without a calculator, so you might want to pick up a calculator and graph it. So if this is a place where you'd want to stop the video and attempt them on your own and then come back and confirm with my graph, you might want to pause the video right now. Alright, so there it is. Okay, this is the graph of that piecewise function. Okay, look at the question. It's asking us what is the limit as x approaches 2 of the function. Okay, so let's investigate behavior from the left and from the right. So let's look at the left-hand limit as x approaches 2 from the left. And I'm just going to use f of x. Okay, however, I could have chosen the appropriate piece. If I'm approaching 2 from the left, that means numbers smaller than 2. So this inequality tells me that I'm on this piece right here. So here's 2. As I approach 2, I'll be walking down the graph here. These points all have x coordinates getting closer to 2. Notice that the y value is going into this open circle of 0. So my left limit is 0. Okay, let's investigate the limit from the right. Okay, if I'm approaching 2 from the right, that means I'm not at 2, 2. I'm on this graph right here. I could use f of x again, or sometimes you'll see the specific piece here. Okay, so the right-hand limit, notice that I'm walking down here, getting closer to 2 from the right. Well, what's the y value I'm going into? It's the y value of this open circle. And if you were to plug 2 into this piece, okay, we see that the open circle occurs at 5, so that's the intended height. Okay, I'm dropping down to 5. So we can clearly see from this that we have a left-hand limit that doesn't equal a right-hand limit, so therefore this is a D and E, back to the question, and you would say because just what we have here, the left limit does not equal the right limit. If I'm approaching 2 from the left, again remember I'm going to use the specific name instead of f of x. Does not equal the right limit. And that piece was 5x over 2. Alright, taking a look at number 17, you might want to, again, like I said, pause, see if you can come up with the graph if that's something that you need extra practice with. Alright, so we have the graph of this piecewise function right here. And you can do t-charts if you want to. I just went ahead and used my background of parent functions to produce the graph. To find this part of the graph right here for the parabola, I just evaluated this piece at 4 and my output was 13. Alright, so let's find this limit. Well, we know it's going to be a D and E because we have a jump discontinuity. To verify it, though, we're going to show that the left-hand limit does not equal the right-hand limit. Okay, if we're on the left piece, we're on 1 over x minus 4. We're going to put in 4, see what results, and we get 1 over 0, which we know that's a D and E. So we have a vertical asymptote on the left. The right-hand limit once you evaluate this piece right here at 4, you're going to get 13. Well, 13 does not equal D and E. So the limit from the left does not equal the limit from the right. Okay, so that concludes finding limits that fail to exist, and at least talking about how to verify or explain that they don't exist.